We're not interpreting pH curves anymore. Sorry, I should have changed that for the last example, but we're in polyprotic acids and bases. My apologies. Okay, so in this example, we are now, I thought we were going to be doing an acid and weak acid and a strong base, but we're still working with the weak base and the strong acid. Now, when we do this, again, focus on the vocabulary of the question if you're unsure which one starts in the sample and which one is being added from the burette. So if I have C6H6O6, 2 minus, okay? If I have that and it says of, okay, that means I'm starting with it. And if it says with HClO4, we are adding it. So in my sample, I start with C6H6O6, 2 minus. And I know it's a weak base because it has a charge -2. All right, we know that weak bases are anions. So I set up my equilibrium and I set up my ice table. The charge becomes -1 because it gains an H. We produce OH. And we need KB. Okay, and I will just tell you what KB is to save some time. Or hell, I'm already here. So K is 1.0 times 10 to the -14 over Ka, which is 2.0 times 10 to the -12. So KB is 5.0 times 10 to the -3. Okay, set up your ice table. You're gonna need a new marker soon. Okay, zeros for the products as always, they go up. Reactant initial concentration of ascorbate is 1.0, goes down, minus X. Okay, so then we're going to set up our equilibrium law, just like we've been doing for a while. That is KB, so 5.0, 10 to the -3 is products, X squared over 1.0 minus X. You guys have seen this before. Time for an approximation. Take your initial ascorbate ion concentration, which is 1, and divide by KB, which is 5.0 times 10 to the -3, should be greater than 1,000. Again, assume it'll always work. Government doesn't want to teach you a different way. But Mr. Burnett, he would realize that this is a simple quadratic formula question. But alas, multiply both sides by the bottom number and then square root. Okay, it's like clockwork now. And we know that X is the concentration of OH in this example, and that is going to be what? Sina, what did you get? I'm assuming now has been enough time. 0.0707 ... moles per liter. Okay. That's not 6, 0. Okay. Because we're calculating OH minus, we can find POH by doing negative log OH minus. And so the POH using negative log, and this number is going to be 1.15 rounded to 2 decimals. Because we have 2 sig digs in the concentration, my pH is 14 minus that, which is 12.85. So I take my math stick, my meter stick, I go to 12.85, which is above 12, below 13, and I draw my dotted line. And not only that, I indicate on my graph that it initially starts, oh, sorry, I drew 13 exactly. It initially starts at 12.85. Okay, we've done that before. Now we're going to go over to the equivalence point, okay? And the equivalence point, again, occurs when you've started to add from the burette and have completely neutralized your sample. So my sample was C6H6O6 2 minus ascorbate ion. I'm adding my acid from the burette, but remember, it's a strong acid, so I really have H3O plus. They're in a 1-to-1 relationship. Single arrow molar coaster, it's going to give us H2O and HC6, H6, O6 minus. Okay? So, concentration of ascorbate was 1. The volume was, I believe 25? Yes, 25 milliliters, so 0.025 liters. Moles is CV, and is 0.025 moles. We're gonna hop on the old molar coaster, rev her up and go. Divide by 1 times by 1, moles is the same. Concentration of our perchloric acid is 0.6, so it's gonna change our number. Volume is N over C, and N over C in this case is going to give us 0.0416 liters. But our graph has units of milliliters, so we want to multiply this by 1,000, and it's going to give us 41.7 milliliters. So I'm going to go over to my graph, 41.7, and I'm going to draw a dotted line going up to represent my first equivalence point. Okay. Now, my final pH only depends on what is left after equivalence. At equivalence, I've gotten rid of all my base, which means the only thing left is my acid. Okay, so I'm going to calculate the pH of my acid, which is HClO4, which we know is a strong acid, so it ionizes completely. So we just write our simple ionization equation. I know you guys are getting unbelievably tired of this, but it's so important to be able to do. Eventually, you're gonna get to the point where you can do it in your head. Hopefully, that's great, that's what we want, because you've been doing it so much. Because the concentration of perchloric acid is 0.6, we know the concentration of H3O is also 0.6 because it ionizes 100%. So if I want to calculate my final pH, I just negative log my H3O or my 0.6, and I'm going to get 0.22. Ooh, super strong. So I go to 0.22 and I draw a dotted line. Okay? Now, to find my endpoint, I take my initial pH, I add my final pH like I've always done and divide by 2. So I'm going to take 12.85 plus 0.22, divide by 2, and that is going to give me 6.54. So I'm going to go over to 6.54, just above 6. I'm going to draw my dotted line. And this makes sense again because I'm taking a strong acid and a weak base, so my endpoint's below 7. Now, remember, to approximate, this is all you have to do, to approximate the second endpoint and the second equivalence point, all we're going to do is double and half, double, comma, and half. So to find your second endpoint, you're going to take your first endpoint and cut it in a half. So that's going to be, I think, 3.27 divided by 2. And to find your second equivalence point, you're going to take 41.7 and you're going to multiply by 2, and that's going to give me 83.4. So I'm going to go over here. I'm going to go to 3.27. Again, approximately. Make sure your axis on your x-axis has a domain of up to about 110, 100. You're then going to go to 83.7, and you're going to draw an axis going up, that dotted line. And then we're going to plot our two endpoints, endpoint 1 and endpoint 2, intersections. Sketch our curve, start at 12.85. Doesn't change, doesn't change, doesn't change, drops, slows down, drops, slows down, and gets back to your initial pH. Make sure it goes through both those points. Now, this right here, guys, we're going to talk about it in the next lesson. This is called a buffer. Be very careful not to draw this line at your endpoint pH, because otherwise this wouldn't look like an endpoint. To be an endpoint, it has to have that sharp drop. But this is called a buffer, and that's what we're going to be talking about in the next lesson.